Welcome back for another exciting session of Calculus 1. We're talking about section 5.6, rates of change. And what we're going to be doing in this section is interpreting integration as accumulation of change. This is harkening back to stuff that we talked about during our very first week of class together. And so I have a major goal for you in this section, which is that I want you to appreciate integration as an accumulation of change. That's what integration does. The integrand, that is the function that we're integrating, is a rate of change. So far, we've been not really attaching meaning to what we've been integrating. We've just been calculating exact areas or approximating areas or computing antiderivatives. Well, now we're actually making the thing that we're integrating mean something, which means that the thing that we get after we integrate means something. So the thing that we're integrating is a rate of change, and what we get as we integrate is the accumulation of change. It's net change, and the derivative is the instantaneous rate of change. So this section really is the one that puts these three pieces together, and I want to bring your attention to one of my Lightboard videos that I made on this topic. The area under a curve is net change. I think I talk about bathtubs in that particular problem. So what I'd like to do is I'd like to just engage in some scenarios with you and think about rates of change and accumulation of change. The first one that I want to draw on is like the net water accumulated is equal to the flow rate times the time elapsed at that particular flow rate. So higher flow means that we're going to have more water, and lower flow means that we're going to accumulate less water. And it's possible that that flow rate could be negative in case that there's a drain, right? So imagine that we have a bathtub, and there's a drain that looks like Florida, and there's a faucet and water in a bathtub. So there's a clawfoot. There's a clawfoot. This is my rendition of a clawfoot tub. Isn't it great? Should have been an artist, JK. Good thing I'm not an artist. Right? So we've got water in and water out. And we can measure the flow rate is the rate in minus the rate out. Because you can turn on the faucet at the same time as you drain the tub. Why not? So the flow rate is the rate in minus the rate out. And if we do dimensional analysis on this, looking at flow rate times time elapsed is like gallons per hour times number of hours, or gallons per minute times minutes is probably a more practical thing to be measuring. It's gallons per time times time. And so I think the dimensional analysis here is quite revealing. So then we can say that net water accumulation is equal to the integral from some starting time to some ending time of the flow rate times the time elapsed. So maybe now you can start to really appreciate what role dt plays. dt, the differential, that's a tiny amount of time. And the flow rate is the instantaneous flow rate. And the reason that I need to do a very tiny amount of time is the instantaneous rate, is because the flow rate changes over time, right? I can turn the faucet on my tub and control the rate, right? So I've got a dial that I can turn, and I can turn it and have more or less, right? Down here is 0. Here is the maximum flow rate. I don't know what direction yours turns in. And so I can vary that by time, right? And so I need to be able to measure the instantaneous flow rate, and then I how long is it flowing at any particular rate? Only for an instant. So dt just represents the accumulation over an instant. And this integral right here, as we know, is just a sum. It's the limit of a sum from some time to some other time. Okay? If we apply this to the world of densities, I might have, let's say a cake, because I've been thinking about making this cake for quite a while now. I really want to make this bundt cake. And it's got these awesome spirals that go around the cake. There's no way I can possibly draw it. We already know I'm not an artist. But this right here, this is a bundt cake. And I really like, you're probably going to hate me for saying this, but I really like cake with raisins in it, or like other fruit, like cherries and stuff like that, right? So the density of the cake varies. It's kind of like if we were to consider the Earth, and what it does, the density of the Earth varies. But we can calculate the total mass by doing an integral. It's the accumulation of the density times a small piece of volume, which we would call dV. dV is the volume element. Right? And I get to say the word total right here because instead of net, I get to say total instead of net, because the density is always at least 0. So there's no way it can possibly be negative. It's guaranteed that net is synonymous with total since the density is positive. Consider the net distance traveled. We've got a particle moving on a line. We've been playing with this kind of scenario, right? So we're going to restrict a particle to a line. We're going to put the origin somewhere arbitrarily, and the velocity is positive if moving to the right, and the velocity is negative if it's moving to the left, right? And so if we consider a particle that's moving and we let it start at the origin, its velocity is positive, and then its velocity is negative, and then its velocity is positive, and then its velocity is negative, positive, negative, positive. Right? It's just moving along that line, and so I'm imagining this right here is the t-axis. So as the particle moves through time, it's also moving in space, and so we can calculate the net distance traveled. So let me shade the areas in blue where it's moving in the positive direction. So there the velocity is positive, velocity is positive, velocity is positive, velocity is positive, and in the other places the velocity is negative. And so the net displacement is velocity times time elapsed. Okay? Writing this in terms of S and V and A, my functions from before, we would have that S of t, no, I don't want the thick lines, thank you so much. We have S of t is equal to the integral of V of t dt, right? Again, I have the instantaneous velocity, and I have an instant. How long is it moving at that particular velocity? For an instant. But it's still, in terms of dimensions, it's still meters per second times seconds. The seconds cancel, and I'm left over with just meters, which is exactly the unit of my S function, my position function. The dimensions work out. We have to have the differential in order to provide the seconds so that it cancels with the seconds in the denominator of the meters per seconds for the velocity. The dt is absolutely critical. This thing right here is a rate. It's got something in the denominator because we're going to multiply it against this dt and they're going to cancel. The total traffic is equal to the traffic flow rate times time, right? We can have cars per minute, say, through an intersection, times the number of minutes that cars traveled through that intersection. And the total traffic flow is going to be the traffic flow rate times time. Cars per minute times minutes, right? Minutes cancels with the per minute like that, and I end up with just the total number of cars. Dimensional analysis leads the way. And finally, one that's really pertinent right now, and one that I think as pleasant as it is to unpleasant as it is to think about right now, the active. Oh, come on, Silviana. The number of active cases. The number of active cases is equal to the new case rate minus the recover rate minus the death rate. So that's the net rate, right? And that net rate is bigger than 0 if more people are getting sick than recovering. And that rate is less than 0 if more people are recovering. Or because we're talking about active cases, the sad reality is that they could actually be dying. So we're thinking about this right now in this particular crisis as a daily rate. We keep getting the number of cases per day. I saw that in early May. This number was somewhere on the order of I'm not gonna give numbers to it, right? But we're giving it. It's just gonna get too morbid. The cases per day times days, right? The cases per day times days is equal to the number of active cases. The dimensional analysis is there for us, and we can write everything in terms of integrals. The cases, active cases, is equal to the integral from the beginning of the crisis till now of the net rate per day times the number of days. Of course, this one's maybe a little bit more problematic than some of the other ones because these things happen kind of discretely in a sense. Cases is an integer number, like we count in whole numbers of days, and this thing right here, we require this thing to be like a differential, and so we really want this to be a dt if I'm going to use an integral symbol right here, and so it's probably more appropriate to write a sum for this particular one, since it's over a discrete number of days. But as I've mentioned a number of times, the integral symbol is also an S. They both mean sum. I've got a theorem for you. This theorem is awesome. This is the theorem that ties everything together. It even has limits in here because there's a limit inside of that integral right there. There's a limit inside of that derivative right there. This theorem is amazing. It says that the net change in some s of t, some state to s of t, over an interval t1 to t2, or if you don't like t's or the variable doesn't happen to be t's, it could be x's, that's fine. The name of the variable doesn't matter. The net change over an interval for a continuous phenomenon is given by the integral from t1 to t2 of s prime. The rate of change is equal to the net change. In other words, in plain English, the integral, the accumulation of a rate is net change. And if you were to take one major lesson out of this entire class, not a practical computational thing, but one lesson from this class, I think it's this. This right here is it. The accumulation of a rate is net change, and is expressed through the integral, through the derivative, and the difference of evaluation of an antiderivative. This is so important. It's so important, y'all. I have a couple of examples for you over the next couple of pages, and then we'll call it good, and we'll pick up with our next 157. So I've got a couple of examples to work through with you. Water leaks from a tank at a rate of 2 plus 5t liters per hour, where t is the number of hours after 7 a.m. How much water is lost between 9 and 11 a.m.? Good question. Okay. Well, since t is the number of hours after 7 a.m., that means that t equals 0 is 7 a.m., so that t equals 2 is 9 a.m., and t equals 4 is 11 a.m. Furthermore, I've got axes. I've got my function 2 plus 5t. We're thinking about a particular time window. That time window. We have this trapezoidal shaped region that we're thinking about. This area right here, that's how much water was lost, is that particular area. We could compute this in two different ways. We could compute this as an integral using the fundamental theorem of calculus part 1, or we could do this using geometry, and we could break it up into a triangle and a rectangle. I'm going to use the fundamental theorem of calculus part 1 because I think it's freaking amazing. So, net water lost is equal to the integral from 2 to 4 of 2 plus 5t dt. Again, I have liters per hour times hours. Infinitesimal hours, but hours nonetheless. That is to say, on the left-hand side over here, I get just plain liters. That's equal to 2t plus 5t squared over 2, evaluated from 2 to 4. Put some parens right there so we know that we are doing this vertical bar evaluated on the entire thing, not just on that piece right there, because otherwise it's ambiguous and a parser would parse it. It's just being attached to that part. That's equal to 2 times 4 plus 5 times 16 over 2 minus 2 times 2 plus 5 times 4 over 2. All I did was evaluate. Let's see here. So I've got 8. I'm going to undo that. So I have 8 plus 5 times 8 minus 4 plus 5 times 2. That's 48 minus 14 equals 34. 34 liters. 34 liters split out. That means that the area over here is, the area of that is 34. Here's another little example for you. I like this next one here. The number of cars per hour passing Wisconsin 37 at I-95 is called the traffic flow rate, denoted Q of T. Groovy. I chose Wisconsin 37 because for some reason, I really like that intersection. It really represents the change going from like Eau Claire out into the country headed toward Durand, and I think the country between Eau Claire and the Mississippi River is really beautiful, and that intersection to me represents that change as I do that drive. All right, so the number of cars per hour passing Wisconsin 37 is the traffic flow rate. So if we analyze this expression right here, this integral from t1 to t2 of q of t dt, we're summing, right? That's all we're doing is summing. The act of summing doesn't change the units. All of the unit change comes from the q and the dt. So I have cars per hour times hours, infinitesimal hours. But the unit is still hours. It's cars. So what quantity is represented by that integral? It's cars through the intersection over that time period. I chose to do this example particularly because of the next part. So we've got the flow rate in cars per hour on 95. And let's suppose that we're recording it at 15-minute intervals, which is not unreasonable. I have read some traffic surveys from when they were redoing traffic timing in my home city in Fort Collins a number of years ago, and they did something like this. And these, maybe I think it was like every 5 minutes that they were giving it to us. It doesn't matter. The thing is that we're taking, they're measuring these rates every 15 minutes, right? Every 15 minutes. And so if we want to estimate the number of cars using the highway during that 2-hour period, then we've got to use this table right here to estimate it. Now, the flow rate isn't 1,044 for this whole 15-minute period. It's not 1,297 for this whole 15-minute period, right? It's varying through that period, but we're only measuring every 15 minutes. So kind of the best I can do when I really want to compute the integral from 7 a.m. to 9 a.m. of q of t dt, but I don't have that. Come on, brain. I don't have that continuously for all t. I only have it discretely at some particular times. So what we're going to do is we're going to approximate this as a sum of q of t sub I times delta t. In particular, we are going to estimate it, let's say using the left endpoints. So that's going to be this part of the box right here. So at the beginning of every 15-minute period, we're going to suppose that the rate was constant for that 15-minute period. And then we'll do it for the right endpoints. So the integral is going to be approximately equal to a quarter, because that's 15 minutes and it's measured in hours, right? Times 1,044 plus 1,297 plus 1,478 plus 1,844 plus 1,451 plus 1,378 plus 1,155 plus 802. And if I mash those buttons through my calculator, let's see here. So I'm going to go 0.25 times 1044. Oh, better open that paren. You know, I think I can do this here. Ooh, that's left over from my last one. Second quit. Clear. All right, so let's do... Yeah, come on. And there we go. Okay, so let's do 0.25 times, I better open a paren, 1044 plus 1297 plus 1478 plus 1844 plus 1451 plus 1378 plus 1155 plus 802, and I am explicitly going to omit that one because it's a right. So I enter, okay. Hang on. I did something wrong here. What did I do wrong? I have a quarter hour. No, I think that's right. I think that's right. Because what I was doing is mentally checking. So like if we think about it, for this block right here, the average flow rate looks like it was maybe about like 1,300 or 1,400, and then the flow rate over this was maybe like 1,200, and that totals together to give us about 2612. Yeah, okay, this seems pretty reasonable. All right, so oh yeah. Okay, this is totally reasonable. Of course, it's 2612.25. I didn't do anything wrong. This is exactly what we were supposed to get. All right. I second guess myself all the time. I think it's one of my strengths. So next, it's really hard to write like that. Let's do the right endpoints. Okay, so we're going to approximate the sum by doing a quarter of the same thing, except I'm going to omit this time that one because it's a left, and I'm just going to take the rights. So 1297 plus 1478 plus 1844 plus 1451 plus 1378 plus 1155 plus 802 plus 542. I can repeat this pretty quickly by going second entry. I'm going to go over plus 542. Do I have key repeat? Yeah, but it's slow. So I'll mash my button over to the left. I want to delete the 1044. My cursor, where did you go? There we go. Delete. Enter. 2486.75. Okay. So somewhere between there, maybe there was like a 10-minute gap that we didn't measure that contained a lot of traffic. And maybe we want another estimate. Maybe we want to average the left and right estimates, and maybe we believe that provides us with an even tighter estimate. I'll leave that to the experts. Next example. So I wanted to do this one because it focuses on the difference between displacement and distance traveled. Like displacement is net. Right? What's the displacement? That's net. Net distance traveled. Like, my displacement when I go for a walk in the morning is 0 because I start and end at my house. Whereas the distance traveled, that's like 1.25 miles as I do the 3-bridge loop. That's the absolute distance traveled. And there's a difference between them. That is to say that the net distance is equal to the integral of velocity, dt, whereas the distance traveled is equal to the integral of your speed times dt, right? Because the absolute value of velocity is speed. Right? Our cars have speedometers. They don't tell us our velocity, they tell us our speed. That's why our odometer measures distance traveled, not displacement. Otherwise, if you leave your house and come back after a long road trip, your displacementometer would read 0, and that would be kind of silly. All right, so let's play with that concept through this example. Let's start by computing displacement for a particle that has a velocity, right? So the particle is restricted to move on a line. If you're tired of particles moving on lines, then take calculus 3. If you're still tired of particles moving on lines after Calc 3, when they'll move on curves, then take a course in differential geometry when we'll talk about all sorts of different things. That course is awesome. All right, so so we've imbued a particle with a velocity, v of t, at any particular time. We'd like to compute the displacement, that is to say, the net distance traveled over that interval. This one's pretty easy. This is equal to the integral from 0 to 6 of v of t dt, which is the integral from 0 to 6 of t cubed minus 10t squared plus 24t dt. Maybe hopefully you're starting to see why I need dt against all of these things, because this entire thing right here has the unit, and dimensionally speaking, I need the times time in order for things to work out. Now I feel weird that I've been writing in red for most of this lecture. I don't know. This is equal to t to the 4th over 4 minus 10 thirds of t cubed plus 12t squared, evaluated from 0 to 6. It's equal to 6 to the 4th over 4 minus 10 thirds of 6 cubed plus 12, 6 squared minus 0. I love it when the bottom thing is 0. It's great. And then I'm going to mash that into my calculator. I'm not going to bring up the digital calculator. You can mash it into your own calculator if you don't believe what I'm doing. 6 to the 4 divided by 4 minus 10 thirds times 6 cubed plus 12 times 36 equals, 36. Neat. Neat. Oh, yeah. I think I just heard somebody light a firework. So, in its journey, we've got a particle moving on a line, and it starts, we don't know where it starts. Maybe it starts over here. And it's moving back and forth and doing whatever it happens to be doing. It's moving back and forth. And then when it ends here at time 6, it's 36 units. I guess it would be 36 units to the right. So I guess it can't have possibly stopped there. When it stops, it's 36 units from where it started. Oh, I made a mistake here. It's 36 units from where it started, not from the origin, because we don't know what its original position was. Yep. I'm leaving those verbal errors in. I'm not trimming those out. All right, so let's compare that to the total distance traveled. So it made it 36 miles from where it started. 36 meters, 36 whatever space units, 36 spaces. How far did it travel in order to get those 36 spaces away? That's going to be the total distance traveled. That's the integral from 0 to 6 of the absolute value of v of t dt, integral from 0 to 6 of t cubed minus 10t squared plus 24t dt with some absolute values. Now, I find that students shirk away from absolute values. And that's okay. No, it's not okay. we're going to deal with it. So remember that abs takes that which is negative and makes it positive, and takes that which is positive and leaves it alone. So we need to plot our velocity function. I think we need to plot our velocity function. V of t, that's equal to, let's see here, t cubed minus 10t squared plus 24t. That's t times t squared minus 10t plus 24. That's equal to t times t, let's see here, can I factor that? 24 has a 6 and a 4 in it. And if I make them both be negative, then I get negative 10, so minus 4, t minus 6. So it's got a root at 4 and 6. Its leading coefficient is positive, and so the function goes like this-ish. That's what it does. So then absolute value, come on, is equal to, that's 6, 4, 0, 0, 4. So that part's still up, but then this next part does that, and then it goes up, like that. Nope, like that. There we go. All right? So it took this negative part, and it was like, whoop, flip it, whoop, flip it. So now it's up. So if we're going to integrate from 0 to 6, now we're going to split this integral right here into two pieces. We're going to integrate the 0 to 4 and the 4 to 6 separately. So I'll be very explicit. Seriously, this was my palm that did that. The integral from 0 to 6 is the absolute value of t cubed minus 10t squared plus 24t dt is equal to the integral from 0 to 4 of, I get to use just regular v of t. I didn't have to flip because it wasn't below. Plus the integral from 4 to 6 of minus t cubed minus 10t squared plus 24t dt, right? So that minus sign right here is the minus sign I picked up by flipping. Okay. Now, I think I want to pull that minus sign out front. I really like that feature. Boop, boop, boop. Equals, let's see here. We've already done this. Seriously, that's my palm. I need to tweak that palm detection setting. This is equal to t to the 4th over 4 minus 10 thirds of t cubed plus 24 over 2t squared. I don't like that. I'm going to replace that with a 12. I did that one step. 0 to 4 minus the same thing. T to the 4th over 4 minus 10, 3, Cool. Alrighty, now we just gotta do it. 10 thirds, 4 cubed, plus 12 times 4 squared, minus 0. That's that thing. Minus 6 to the 4th over 4 minus 10 thirds 6 cubed plus 12 times 6 squared minus 4 to the 4 over 4 minus 10 cubes of 4 cubed plus 12 4 squared. Boop. Yes. I think we already computed one of these numbers before, didn't we? I think we did. I think we computed this number before. And I think we found that that was 36. Yeah, we found that this was 36. I'm not recomputing that. So now I just need this number, and fortunately it appears twice. So I'm just gonna, the ands trick would have been really handy here, because then I could just go 4, enter, second entry, enter, and I would just have it. Whatever. 4 to the 4th divided by 4 minus 10 thirds times 4 cubed plus 12 times 16. 42.666666. Yeah. Okay. These do not cancel because I got a double negative. So I got to go ands times 2 minus 36 equals 49.333333. And that's the total distance traveled in order to get there. So think about it. Focus on these two diagrams that we drew that are the velocity and the speed. The velocity and the speed. When we computed the integral of the velocity from here to here, we had the area up here where it was moving forwards, and then the time down here when it was moving backwards, right? And those two regions together, with the one down here being negative, added up to 36. And if I take this one right here, it's positive. And then this one right here we're counting as positive, because we're just thinking about the speed that it's traveling at. Not whether it's moving toward or away from the origin. We don't care. We just care that it's moving. And we found that those two areas together were 49.3 with a bar over it, which means that this little area right here was 13.3 with a bar. And you can double check that fact. You could integrate either one of these two things, and you'll get either positive or negative 13 with a bar, 13.3 with a bar. Okay. Groovy. I wanted to do one last example with you, which is another water problem. So water flows in and out of a small holding pond at a rate of 210 sine of pi over 12t plus 139 meters cubed per hour. How much water is accumulated in the pond during the first 3 days? So t is measured in hours. So during the first 3 days, that's the time window from 0 to 72 hours in the first 3 days. So we want to know the integral from 0 to 72 of 210 sine of pi over 12 times t plus 139 dt. And now I'm guessing as we go and do this, you might rebel that we haven't done that yet. But I posit that because you can differentiate that, you can integrate it. Because if you were to differentiate this, you would have to chain that thing out. So when we integrate it, I've got to compensate for that. And we'll be able to double check that. So let's write this as the 210 times the integral from 0 to 72. Nope, let's go ahead and do the integration. Let's go ahead and do the integration. And I think you're ready for it. So what do I differentiate to get sine with a positive minus cosine? And I'm careful to open that paren one that I just did. Otherwise it looks like 210 minus cosine, but it's not. It's 210 times minus cosine. And now I've got to correct for that. So if I were to differentiate this, I better get my original thing back. So I better put a 12 over pi right there. plus. Are you with me? If not, then you should totally ask about this in one of our class discussions, or I would suggest have a 210 against too many things. There we go. Or I'd suggest wait for our next packet when we're going to do that more formally. Okay. So if you don't believe me, I would recommend integrate this with this prefactor right here. So, sorry, not integrate. Differentiate this, and you'll get that. Okay? So, I've got 210 times 12 over pi with a minus sign times cosine of pi over 12 times 72 minus cosine of pi over 12 times 0 plus 139 times 72 minus 0. I'm not going to write the minus 0. All right, I'm just going to take a second and look at my work and make sure I didn't make mistakes, because it's possible. That's why I offer rewards for finding my mistakes, because I make them all the time. So this minus sign is this minus sign. I simply pulled it out front. I made sure that my 210 was only against the cosine part, not against that part, because the 210 right here is against the sine. So that checks out. Yeah, things are looking pretty good. So this is 210, totally relying on my calculator. 210 times 12 divided by, divided by pi. Now I've got to do this. This is 3 times pi. This is, let's see here. Oh, the stuff inside there is, I can tell I'm getting tired, 0. Ooh, cosine of 3 pi is the same thing as cosine of pi, so that's minus 1. And then this part back here is 1. Ooh, so that's minus 2. Ooh, this is good. Okay, so the minus plus. So I'm going to multiply that by 2. $139 times 72. 10,008. 10,008 plus 1604.282 is equal to 11612.282 cubic meters. So there's kind of like a constant flow rate and then a part that modulates, a part that oscillates. There's oscillatory flow rate and then there's a constant flow rate. The constant flow rate was like 139 for 72 hours. And then this other part here was going up and down, right? It's going up and down, and the magnitude of that wave, the magnitude of half that wave is 210. The magnitude of the trough to crest is 420. And the period of this is happening every 24 hours. Right? No, every 12 hours. Oh, my mind is not working. I need to go to sleep. Okay, so let's sketch and graph the rates of the flow rate and the accumulation function. assuming that the rate. So over here on this one, I'm going to plot R of t, the flow rate. It's offset by 139, and the units of this axis is meters cubed per hour. And the flow rate's not constant. It starts at 139, but then it goes up. And as it goes through 12 hours, it's going to go up through sine, and then through 24 hours, it's going to go back up. And then after 36 hours, it's going to go up and come back down. So there's kind of this like average flow rate of 139. And then there's like, sometimes it's flowing higher and sometimes it's flowing lower. And sometimes it's flowing higher and sometimes it's flowing lower. Except that I've drawn this incorrectly because this distance here needs to be 210 and it's not the way that I've drawn it. So I need to try that again. So let's try that one more time. So I need the average to top to be 210. So sometimes there's flow out, but most of the time there's flow in. Most of the time there's flow in, sometimes there's flow out. So if we think about the accumulant function, this R accumulation function, the net water flowed function, we're saying at first it started at 0 because this is the R axis. That's the net water. That's the time axis. And so as we move over here, we're sweeping out lines and we're integrating up to that line. And at first, no water has flowed. So I set the initial condition R of 0 equals 0 to say that, well, at first, no water has flowed. So it's increasing, and then it's increasing faster, but then it's increasing, and now it's increasing slower. So it's increasing, and it's increasing faster, but then it's increasing slower, and then it's eventually levels off. And it levels off right there sometime after 12 hours. And then it's going to go down for a little bit. And it's going to go down until, for some period between 12 and 24 hours. It's going down. And then it's going to go back up again. And then it's going to do that same thing over and over again. And it's going to go back down, and then it's going to go up, and then it's going to go down some, and then it's going to go up. So, the general trend is in the up direction, but sometimes it flows down, right? Sometimes it's going in the down direction, and that's where the rate is negative, where water is flowing out of the pond during those time periods. Most of the time, water is flowing into the pond. Sometimes water flows out of the pond. When water is flowing out of the pond, the accumulant function is decreasing. When water is flowing into the pond, the accumulant function is increasing. I really want you to work with and practice that, because that is the qualitative skill that I want you to take away from this. And it's so immediately applicable to these plots that are governing the very safety of our lives right now when we're talking about COVID-19 infection, recovery, and death rates. I think that you really need to be able to pay attention and understand these things, because it is so incredibly important to be able to take scientific and numerical control of our lives in the face of adverse forces who don't want us to apply science to take control. I don't have any more pages to add to this. That's all I wanted to say about rates of change and net change. I think the title of this section was actually net change, so I think that was a mistake. I'll fix that extra word that I had earlier before I post and say thank you so much. I really appreciate your time, and we got 2 sections left. That's it. We just got 2 sections left. You can do it. We got this. Catch you later. Bye.